Louis Hahn. I'm a PhD student at the University of Waterloo. I study here at Kitty Lab. We work with trapped ions to study quantum systems.
Louis Hahn is helping develop one of the newest technologies in computation since the invention of the electronic computer. Like the original computers that were built after the Second World War, these quantum machines are experimental and fragile, but they promise a whole new frontier in computation. Quantum computers come in all kinds of designs, but what they all have in common is something called a quantum bit, or a qubit. Qubits are different than the classical binary bits in your home computer. Just like a simple light switch, classical bits can only be in two states, off or on. These two states are the binary zeros and ones that your computer uses to perform all its calculations. Qubits are something different. They are made from quantum objects, like single atoms or photons, whose behavior belongs to the quantum world. Under the right conditions, a qubit can exist in states called superposition, where the value of the qubit is neither a definite one or zero. Instead, it is in a state defined in terms of the probability of it being a 1 or a 0 at the moment it is measured. This allows for calculations based on interacting probabilities that unfold over time in order to solve complicated problems that even the largest classical computers find very hard to do. Another feature of qubits is their ability to store exponentially more information than classical bits.
For classical computers, if you have a bit, you could either store 0 or 1. For quantum bits, since it's in superposition of 0 and 1, you have two parameters there. The probabilities of being in 0 and probability of being in 1, right? There are two parameters, right? You could store information in those two parameters.
Right, so if you have two qubits, you can basically store or manipulate 4 classical bits of information. If you have 3 qubits, you can manipulate 8 classical bits of information. And so if you keep adding them, you can manipulate an exponential number of classical bits of information.
The same quantum behaviors that make qubits so useful also makes them very difficult to work with in functioning quantum computers.
Quantum systems are very fragile, and they lose their quantumness as long as they interact with the environment. So in order to keep them quantum, you need to keep them separated from everything else.
Louis and his colleagues are approaching the challenges by using a technology called an ion trap.
In front of me here is all the optics and enclosures needed for trapping ions and performing quantum simulations on them. So we start out with a vacuum chamber, which we use to trap the ions. Inside the vacuum chamber, we have this little stainless steel tube that we've placed this metal ytterbium in. By passing current through one end of the tube, it heats up and neutral atoms are going to start flying out of this tube. And we've positioned the tube so that it is pointing towards the center of the trap. In that chamber is what's known as a 4-rod Hall trap. So it consists of 4 rods in this configuration and 2 needles at the ends. And this is what confines the ions to a specific point in space. In the center of the trap, we shine a laser that ionizes the atoms we care about. And so once they're ionized in that center of the trap, they're basically trapped there.
Both trapped and cooled, the ions are now qubits that can be programmed into superpositions that allow them to solve problems.
So now that we have sort of a chain of ions, we now want to do something with them, essentially. And to do that, we typically shine lasers on those ions. So there's tons of laser and optical systems here to prepare the light in such a way that it'll talk to the ion to do what we want to do in some experiment. When we're detecting these ions, we've collapsed their state to either the 0 or the 1. And that collapse happens in a statistical fashion. So there's some probability of it collapsing to 1 and some probability of it collapsing to 0. And so when we detect it, one experiment doesn't really tell us any information. We have to repeat that many times. So yeah, it's a really interesting time right now because we're at the border of being able to simulate systems that we just can't do classically.
Quantum has lots and lots of applications tied to it. For example, the supply chain, any company diverting their supply chains, or maybe a postman posting letters at various places, what shortest route it should take?
Definitively is very exciting, especially when you think about some of the hardest problems that we cannot really solve right now with the technology that we have. Simulating time evolution of different kind of molecules, the interactions, this is really difficult. That's where you really have this remarkable computational power, simulating quantum system on a native quantum device. These kind of problems are the problems that the whole humanity has.
The promise of quantum computers lies in the ability of qubits to simulate the true complexities of the world around us. They won't replace our classical computers. They will tackle a whole new domain of problems that, until now, have been out of reach.